let us see the flow measurements through the pipes and channels. So in order to measure the amount of the flow that is taking place through the pipe, we want to calculate what is this particular flow. That particular flow can be evaluated. Suppose if this is the pipe, this is the pipe, a horizontal pipe, and we want to know the quantity of flow. Let us say Q is the discharge flowing through the pipe. In order to measure what is the value of this Q, that is the rate of flow, and we want to use a venturi meter in a portion by cutting. So this portion of the pipe is cut and we can install the venturi meter, and this venturi meter is a device used to measure the rate of flow. And this venturi meter is invented by G.B. Venturi. This venturi meter works on the principle of Bernoulli's equation. So the principle of this venturi meter mainly works on the principle of Bernoulli's equation or energy equation. And let us see the principle of this Bernoulli's equation. Now you can see, as I said here, the venturi meter you are going to fix here. Let us take, this is the pipe, and a venturi meter is like this. So this is the venturi meter. So this is the pipe, and this is the venturi meter, and this is the flow. We want to measure what is the value of Q that is flowing through this particular pipe. So I cut the section and install the venturi meter. So this is the inlet portion followed with convergent. So this is the convergent portion, and this is the throat, and this is the divergent portion, and this is followed with the outlet. So the basic principle on which this particular venturi meter works is the principle involved here. We are creating the pressure difference between the 2 points. This is the section 1,1 and this is the section 2,2. So here you can observe the pressure P1, V1 and Z1, the pressure velocity datum. Here P2, V2, Z2. So the measurement of the pressure is done by means of using the manometer. So manometer is a device used for measurement of the pressure, and this particular pressure and this particular pressure, here the pressure is more, here the pressure is less, and accordingly if I apply the manometer and I connect to the venturi meter. So the features of this particular venturi meter has, you can see here the diameter is d, this diameter is small d, and create the pressure difference. I connect the manometer. This is the manometer. Manometer is a device used for measuring the pressure difference between the 2 points, and before the flow, this manometric liquid is here. So before it connects to the pipe, as per the pressure formula, H is equal to P by rho G. So the pressure head here and here, they are same. If we take these points, this one, both are same. because the liquid, the density is same here, G same, P same. So this particular one, before it connects to this pipe, the manometric level is horizontal. And once it is connected to the pipe, the flow is passing through this venturi meter. As I mentioned, here the pressure P1, here the pressure P2. So P1 is greater than P2, or the difference of this particular pressure is indicated by a manometric head. So let us consider this is the X, the difference of the manometric liquid, and this difference of the manometric or difference of the pressure head, and X is the pressure head or venturi head, we can say. So this H can be calculated by using the value of X by applying the Bernoulli's equation, and the Bernoulli's equation states that the total energy remains constant. That means the energy at the section 1 is same as the energy at the section 2, and neglecting the losses between these two sections. This is 1, this is the section 2. So this point. So according to this particular one, the pressure P1, V1, Z1. So P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2. So this is the Bernoulli's equation. Applied the Bernoulli's equation between these 2 points and neglecting the losses from this point to this particular point. So the neglecting the loss, I have applied the Bernoulli's equation. Accordingly, this Z1, Z2, this Z1, Z2 are the datum heads. Means by position, anything with reference to a datum. Suppose if I take this one is datum, if I consider this one as datum, so this point 1, this is the Z1, and this particular point 2, this is Z2. So this is the Z1, Z2, the datum heads, and if I consider the center of the pipe as datum, center of pipe as datum, this particular point, this is the center line, this particular point as a datum. So this Z1, Z2 will get cancelled because Z1 is equal to Z2 is equal to 0. So these terms will get cancelled. Now the remaining equation here, P1 by rho G plus V1 square by 2G is equal to P2 by rho G plus V2 square by 2G. Now P1 by rho G minus P2 by rho G is equal to V2 square by 2G minus V1 square by 2G. Now, according to the formula, P is equal to rho G H, P is equal to rho G H, H is equal to P by rho G. That means P1 minus P2 divided by rho G is equal to 1 by 2G into V2 square minus V1 square. Now, this P is equal to rho G H, P1 minus P2 or P by rho G is nothing but the pressure head. So this pressure head, you can write H is the pressure head between these 2 points 1 and 2. This pressure head can be calculated by knowing the difference of the mercury levels, and this H is given by now 1 by 2G into V2 square minus V1 square. And as I mentioned, the Q, the discharge flowing through this pipe, let Q theoretical is the theoretical discharge, which is equal to, according to the continuity equation, Q theoretical is equal to A1 V1 is equal to A2 V2. That means this particular sectional area at this particular section 1, 1, A1 is the area at section 1, A2 is the area at the section, V1, V2 are the velocities at 1 and 2. So according to the continuity equation, Q is equal to A1 V1, and hence I can write this one, V1 is equal to Q theoretical divided by A1, so V2 is equal to Q theoretical divided by A2. So substitute back in this equation, P1 minus P2 divided by rho g, 1 by 2g, into V2 square, that is Q theoretical square divided by A2 square minus Q theoretical square divided by A1 square. So this is H is equal to this particular one, Q theoretical square divided by 2g into 1 over A2 square divided by 1 over A1 square. Now this equation I can simplify further with reference to the H is equal to Q theoretical square divided by 2g into, this is A1, A2, so A2 square minus A1 square, A1 square minus A2 square divided by A1 square, A2 square, and Q theoretical is equal to square root of A1, A2 divided by root 2g. So this equation Q theoretical is from this one 2gh, this particular equation we can write square root of A1 square minus A2 square into root 2gh. Now we can see this particular value. This is the equation for calculating the discharge through the Venturi meter. But I mentioned here the Q theoretical discharge. Since I have not considered any losses here, the losses are not considered here. So whatever the discharge we say, it is a theoretical discharge, but the actual discharge is always less than the theoretical discharge, because always there is a loss between the 2 points. This loss I have not considered initially. If I consider the real or actual discharge, so actual discharge is equal to coefficient of discharge into Q theoretical, and accordingly the value of Q actual is equal to CD into A1 A2 divided by square root of A1 square minus A2 square into root 2gh. So this is the discharge flowing through the Venturi meter. The coefficient of discharge is the ratio of the actual discharge to the theoretical discharge. So this is the equation which can be used to compute the flow through this particular one, the flow through the pipe. So this is the concerned equation can be used to calculate the value of the actual discharge. Now you can see this particular H here. This H is the Venturi head. This Venturi head can be calculated by applying the manometric equation. This Venturi head can be calculated by applying the manometric equation, the pressure at this point, the pressure at this point, equating the two pressures at this particular point, pressure from this limb and the pressure from this limb, equating this one. The value of X is equal to Sm by S0 minus 1 this is the into H is equal to X into S naught minus 1 minus Sm by S naught. So these are the equations. When you apply the manometric equation, that means apply the pressure at this point is equal to, that is pressure in the left limb is equal to pressure in the right limb. So equating this one, you can calculate the value of H here. That means Sm is equal to specific gravity of manometric liquid and S naught is equal to specific gravity of the flowing liquid. That means we can see the flowing liquid, the liquid which is flowing through this particular venturimeter, if this is a lighter liquid when compared to the manometric liquid, so this is the value of H you can use, and if it is, this is the heavier liquid when compared to this one, this is the equation. So now using this particular one, knowing the just the value of the H, that is the differential pressure head or venturi head, we can use in this particular equation, all these particular terms are constants. That means the value of Q, the value of this Q can be, this whole term is constant, so I can write Q is equal to CD into some constant into root H. So the coefficient of discharge is also a constant value, so this whole term becomes again the constant K1. So Q is equal to K1 into root H. So you can plot a graph between Q versus root H, Q versus root H. You can plot a graph of the form y is equal to mx, and you can calculate the slope, and using the slope you can estimate the value of CD, that is the coefficient of discharge. So this K value, as I mentioned, K is a constant. This entire value, that is A1, A2 divided by square root of A1 square minus A2 square into root 2g. So the A1, A2, these diameters are fixed here, this throat and the inlet diameter, g is the acceleration. This entire term is a constant, so this particular become CD is a constant, so K1, that is the total value CD into K is equal to K, and K is known, and you can calculate what is the value of the CD. Once you plot this particular graph, you can get it the value of what is the value of the coefficient of discharge. Now, these particular properties you can observe the venturimeter. As far as the venturimeter, you can see I created a pressure difference between these 2 points. With respect to this particular pressure difference, certain important parameter you have to consider here, the diameter of the throat section. This diameter, the throat diameter here, so we can see this particular venturimeter, the basic principle on which this particular venturimeter works is the creation of the pressure difference. That means the value of this X. Means if you reduce the diameter, D is the diameter at the inlet, diameter of the inlet, and small d is equal to diameter of the throat, the diameter of the throat, that is a small d. The very important feature, characteristic feature of this particular venturimeter is, by creating your equation Q is equal to some CD into K into root H. and you create more and more value of H, the pressure difference H is equal to X into specific gravity of manometric liquid minus 1. If the value of X is more, that means automatically the H is more because Sm and S0 are the specific gravities. But if the pressure difference H is more, it can measure very accurately the discharge. Q can be measured more and more accurately measure the discharge. But the pressure at this particular point, if it goes on decreasing the diameter, one particular stage, the flow is not possible. That means if this pressure difference, let us say this particular point according to the Bernoulli's equation, P by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g is equal to some constant. The total energy remains the constant. Let us consider this energy is 6, this energy is 4. Let us consider this energy P2 is 3, V is 7. Let us consider these values of just pressure and velocity. So you can see the pressure difference. Because this pressure is more than this particular pressure, because the pressure at the section 1 is more than the pressure at the section 2. Naturally, this fluid will flow above. That means at section 1 the pressure is more compared to section 2, therefore the manometric liquid rises to the right limb. So this particular pressure difference P1 is more than P2. The difference of 6 minus 3 is equal to 3. The pressure difference is 6 minus 3. And further you reduce this particular diameter, if you reduce further, this is a constant because it is equal to the diameter of the pipe. And this particular section, this diameter further if you reduces, this is a constant 6 plus 4 because this is the inlet. And I am reducing the diameter further reduces. So when it further reduces, this particular pressure decreases. Let us say this is 2 and this is 8. And the pressure difference you can see 6 minus 2, this is the 4. Like this, you goes on reducing the diameter, you can create more and more pressure difference. But if this particular pressure difference, if the pressure falls less than vapor pressure and this particular point, the flow is not possible. Because if the pressure falls below this vapor pressure, where the boiling of this liquid, and that particular point, due to the diameter very small, inside that one the flow is not possible, means inside that air is present, the suction pressure will be there. Once the suction pressure develops, this suction pressure forms the bubbles in the liquid. That means when the flow is taking place, the bubbles will form. The bubbles will form in the liquid, and these bubbles will not continuously form. The bubbles will form and the bubble will burst. Once the bubble will burst, it exerts very high pressure. This bursting pressure, if it is more than the pressure, the maximum pressure of the pipe, so naturally the pipe subjected to the cracks. That means the throat point where you are having a material, this material is subjected to the cracks and failure of the venturimeter takes place. So this formation of alternate formation and collapsation of the vapor bubble, technically known as a cavitation. So cavitation is a phenomenon of